So some of you may have noticed outside it talks about a distributed model talk. So you might be a little surprised seeing the ML pipeline stuff. Actually, what happened there was I submitted that abstract back in early spring. And then this summer, we actually released MLflow. And the big thesis from that talk, I ended up getting scooped by the MLflow team. But since then, I've done a lot of close work with the MLflow engineering group. And that led to this current talk. So who am I? I'm a solutions architect with Databricks, mostly focused on machine learning and deep learning. Previously, I was a data scientist at McKinsey and then a machine learning engineer at Quantum Black. We worked on a lot of different projects in many verticals: healthcare, telecom, mining, renewable energy. So lots of cool stuff there. Before I get started, just to get a sense of the crowd, so please raise your hand if you identify as a data scientist. Awesome. How about data engineer? Machine learning engineer? Something else I didn't name? OK, cool. So mostly data scientists. The goal of this talk is aimed mostly at data scientists. Basically, the idea is first to call out a big problem that I've noticed in data science and production. Namely, essentially, the main issue with data science that I keep on running into again and again is an overfocus on models, when it's actually the glue code and the plumbing that you run into issues. So the beginning of this talk will be kind of setting that problem up, as well as giving some practical tips to solve this issue in production. And then I hope to use the end to actually discuss why is plumbing actually the issue, and where do I think machine learning in production is heading. So we've all seen the hype around AI delivering lots of value, and you're all here partially because you've realized some of that value. But I'm also sure that a lot of the data science groups here have run into issues. A lot of these issues come in the form of data scientists using scikit-learn and Keras, whereas the data engineers are using Spark and Scala. And they're wondering, how do we combine the two? Whether it's getting the data into scikit-learn, how do you go from distributed to single node, or actually taking those models out of single node and then actually deploying them. So you've probably seen this paper. This came from Google back in 2015. That machine learning is a high-interest credit card of technical debt. And their whole point was, when it came to actually deploying machine learning models, the actual ML model was a very small part of the whole system. It was actually all the stuff around the ML model that turned out to be quite difficult. If I remember correctly, they were actually just doing a basic logistic regression in this example. But there was a lot of complexity even with that. So where does this complexity around plumbing actually come from? So I mentioned there's this silo between the data engineers and the data scientists and the machine learning engineers. Part of it's tooling, part of it's distributed versus single node, part of it's culture. There's a lot of different aspects. Here's how we've been working on trying to make this simple. So the thing that we're not trying to do is go to data scientists and say, hey, you should stop using scikit-learn, or whatever R library you're using. You should exclusively use Spark ML. When the original co-founders of Spark first came out with MLlib, the idea was, OK, well, just have data scientists move to MLlib, problem solved. But of course, this doesn't work, because data scientists need to try out new models. And you don't a priori know which model is correct for your problem, so you need to try out many things. So that doesn't work. Also, what I found in my previous life as a data scientist and machine learning engineer is that data scientists can be stubborn switching to new systems, and actually rightfully so. There's a non-trivial cost to switching to a new system versus doing what you know. You're very productive in R or Python, and trying out some new system, whether it's a new microservice, Docker, whatever you name it, takes a long time to learn, and that's a big productivity hit. So what I've basically found is, if you want data scientists to switch to a new system or try something out, there are basically 3 rules that you got to hit. 1, your new system has to deliver at least 10x the value in some form. 2, you have to be able to show that value in 3 steps or less. And then 3, you have to show that value in about 60 seconds or less. So what I found is if I only get 2 out of 3 of those, I actually can't get people to switch. But if I can get all 3, then it seems like super obvious, and people will change. So what I'm going to be showing you next is a few examples of things that we've been developing that I think actually hit all 3 of those things when it comes to data science pipelines, with the hopes that this will help you get a massive increase in your productivity. So the 4 examples, ML runtime, pandas vectorized UDFs, distributed transfer learning, and MLflow, a lot of these were actually mentioned by Michael Armbrust in the keynotes, but I'll be doing a little bit more of a deep dive. So to start with the Databricks runtime, it's very common for data scientists, as they're trying out many different libraries, to constantly install stuff, but then that leads to a few different issues. One is, how do different data scientists collaborate in the same environments? You might try Conda, which is pretty popular, but then you find that certain things you can't really install very easily with Conda. Maybe you need to use pip. Or recently, Conda changed this, but it used to be for GPU integration for TensorFlow, you'd have to install CUDA libraries separately. So managing environments has been a big pain. Furthermore, once the data scientist sets up their environment and comes up with some models, if they want to hand that off to the production engineer, that turns into an issue as well. And so we start seeing solutions where people try out Docker and Kubernetes and other things in order to standardize the environment. But then that leads to a lot of complexity and overhead on the data science team. So to solve this, we created a set of clusters on Databricks that just come preloaded with all of these libraries. Of course, you can install any other library you want, but being able to just select a cluster with all these libraries ready to go means the data scientists don't have to spend all that time installing this stuff. You don't have to worry about different data scientists being in different environments. And furthermore, when you want to productionize this, the data engineers can just select that environment, and it's ready to go. Furthermore, we have GPU support. So if you want to try this out on GPUs, again, you don't need to worry about installing your linear algebra libraries. You just select the GPU version, and it's ready to go and optimized. So this feature has been growing extremely fast in terms of usage. But I think the big idea here for your teams is, what are the things that your team is doing again and again outside of the modeling that you can actually standardize? And installing environments and standardizing environments is a huge one. So the second one we're going to talk about is vectorized pandas UDFs. The big idea here is maybe the data engineering team has been working with Spark, and they have some data pipelines that the data scientists want to start working with. At this point, there's a really common pattern where data scientists will try and sample out the data and then run it single node, either on an EC2 instance or their laptops. The problem, of course, is when you're going from distributed to single node, you have to really downsample. And even then, converting to pandas can be a pain, because pandas is a huge memory hog. It can often take up to 20 to 50 times the amount of memory allocated for that data just when loading to pandas. And in fact, the creator of pandas, Wes McKinney, published a blog post a little while ago called 10 Things I Hate About Pandas, and he talked about the memory problem being one of them. So what we did to solve this is we integrated Apache Arrow, a columnar-based format, into our underlying code. So when you write from Spark to pandas, it converts to that vectorized PyArrow format rather than raw code. So let's see what that actually looks like. OK. Can you all see that OK? Looks good. OK. So here I'm just grabbing a basic data set, mortgages data. It's actually about 2.5 gigs, nothing fancy. And what we're going to do is we're going to try and convert this data set, which is loaded in Spark, to pandas. So first thing you'll notice is that I'm actually turning off arrow support. So now it's just using plain text. And if I try and do dataframe.toPandas, this actually gives me an out-of-memory error. So that's no good. I actually need to sample it down to just 1 million rows. And then it takes about 25 seconds. Once I turn the Apache Arrow back on, now I can actually take the whole mortgage data set to Pandas, no problem. And now it's only taking less than 10 seconds. Now this is pretty good because the original data set was about 17 million rows. So we just wrote out 17x the data in less than half the time. Great. So big takeaway here is if you're a data scientist and you're trying to go from that distributed to single node, you got to be using this Apache Arrow vectorized format. It's just a no-brainer. And in fact, the more complex your queries, the better performance you're going to get, sometimes going over 100x speedups just from this. We also incorporated this into making more efficient user-defined functions. So in the past, people could take something like Python and R and run it as a Spark UDF. But it was horribly slow because it was working element-wise. And in this case, you can see I'm creating a simple function that just adds 1. And this takes about 2 seconds. We can simply replace UDF with pandas UDF. And we see, OK, now it takes 0.3 seconds. Going back to this idea of 1 step, right? Less than 60-second change, more than 10x the value. This is a no-brainer, right? You just go through your UDFs and replace them with pandas, and you get a huge speed up. But again, the more complex our queries, the bigger the speed up we see. So here we're using CDF simply because it's an arbitrarily complex function. And we see with the regular UDF, it takes 32 seconds. And with the pandas vectorized UDF, it takes 1.5 seconds. Not bad. So if you're not using pandas vectorized UDFs, and Apache Arrow in your data pipelines, you're missing out on huge performance for a very small change. OK. Oh. OK, so next up, I want to talk to you about deep learning pipelines. So this feature came out, I believe, back in 2017. And the idea was, how do we make deep learning even easier on Spark, both for transfer learning and for serving, actually? A lot of teams look at deep learning, and they find it very intimidating, both from the perspective of, well, do I need to be a deep learning expert in order to make these architectures from scratch? And then also, let's say we do have deep learning experts on our team. How do we possibly deploy this? It's challenging. So our question was, how do we take deep learning and make it available to people who are not necessarily deep learning experts? One part of this is that we can utilize something like transfer learning to add features to our data from pre-trained nets. And then we can take that featureized data and send it through a simpler machine learning algorithm, such as a logistic regression, to take advantage of those pre-computed features. That simplifies deep learning, but it also allows us to use best-in-class models. On the production inference side, we can actually take a serialized deep learning model and register that as a user-defined function. Once it's registered as a user-defined function, you can use it in Scala, in Python, in SQL, and in R. So you can actually see in the example at the bottom of the screen, we have a trained Keras model. And once we register it as a UDF, anyone in the organization could then use it as a SQL call. That's how you democratize machine learning algorithms. And this is going to tie into one of the deployment strategies for MLflow as well. So let's take a look at what this actually looks like in practice without closing all my tabs. OK. So in this example, we're going to be taking in some CCTV footage, and we're going to use our trained deep learning net to pre-process the data and add those features. We're then going to take the Featurized data set through a logistic regression to predict if a video is suspicious or not suspicious. So I may not be getting internet, but you can believe this is a CCTV video. Basically, the first thing we do is we extract out the images. So here you can see the individual frames from the video. Next, we're going to load this into the Spark deep learning pipelines. This creates a special deep learning Spark data frame, as you can see right here. The next step, this is where the magic happens. We're going to apply our featurizer, and we're going to do it by downloading a pre-trained Inception v3 network. This is built on top of Keras, so all the pre-trained networks in Keras are provided here. Now, this is great because we're grabbing best-in-class deep learning from Google and other companies applied to ImageNet, except what we're doing is instead of applying the whole deep learning algorithm all the way to the end classification, we're actually just cutting off that last classification layer and using the second to last layer, which provides abstract features, which we then use to transform our image. So these are not human interpretable, but machines love it. And after which we just write to Parquet. So once we've written to Parquet, it's time for the next step. We load that Parquet data, and now we're just going to use a simple Spark logistic regression. That tells us suspicious or not suspicious. We add a bunch of existing labels, and we're then able to pull that out of our data and figure out, OK, is there any suspicious data or any suspicious frames? Yes. Boom. OK, we can go through and say, yes, actually, this did pull out suspicious stuff and gave us quite good performance. So we're able to use best-in-class networks without having to be deep learning experts. And furthermore, once we produce something like this, it's inherently scalable because this logistic network is running on Spark. If you wanted to use a pre-trained network and then use transfer learning to update it to something specific, again, you can simply serialize that to some format like .h5 or MLeap, and then use a Spark UDF to apply across many distributed data sets. So I think this is a really powerful pattern that I've seen various companies use successfully, even if they aren't deep learning experts. So now MLflow. MLflow, rather than being focused specifically on individual models or model serving or anything like that, is really supposed to be a general open source framework for ML lifecycle management. And it came about by looking at some of the reoccurring pain points that data scientists and engineers were experiencing. For instance, logging. Logging is so important, and yet I think most of the data scientists I know, myself included, either really hate logging or we've come up with our own very unique logging solution that doesn't generalize super well across teams. Or the engineering group has enforced some logging standards on us, but it's not really applicable to our workflow since it's coming from engineering and not data science. Huge pain point. So the first part of MLflow seeks to solve that by making logging super easy. Just allows you to import MLflow and then do MLflow log params, log models, log artifacts like plots. Solved. And what that does is it takes those things, bundles it up into a very lightweight format with basically a YAML file on top of it, the ML project file. And then you can look through all of your stuff via a UI or actually deploy later on. So let's see here. That's called MLflow tracking. I'm running a little short on time, so I'll actually just jump into the demo for that. So here's what it's actually going to look like in practice. MLflow, again, you can just pip install it. Extremely lightweight. This is a basic scikit-learn problem where we're predicting some diabetes factors. So the first entry point into MLflow, you're going to see with MLflow.startRun. So that's how we specify a single model run. If we're doing something like hyperparameter tuning, this is currently a weak spot. Usually right now people are doing nesting, but we're looking into coming up with a map solution rather than nests. But whenever you have this with MLflow start run, it will start tracking everything within that run, and then you can view the results on your UI. And then you can actually see within the run, I have MLflow log params, log metrics, log model, and then also log the artifact. So all of these are going to be packaged together, along with what versions of libraries I'm going to be using in this ML project format. The benefit of which is that if this is saved under GitHub or Bitbucket or something like that, we'll actually be able to completely rerun this experiment by saying MLflow run and then passing that git commit hash. And then if we go down to the bottom, so this is what the UI looks like. You can either run this yourself or in Databricks, as you saw Michael doing earlier. This is what each of those artifacts comes out to be, a little package that you specify. Usually we save it on S3. And then this standardized package makes it very easy for production engineers to deploy experiments without having to know anything about it. One of the goals of MLflow is to be agnostic to different models. Right now, it's not totally agnostic, but it does support a large range of models, as well as allowing you to create your own flavors for new libraries. With the newest version of MLflow that was released earlier this week, they allowed arbitrary Python deployments. So hopefully this will get us a bit further towards that arbitrary model deployment. This is still very alpha, but we've seen a big uptick with our larger companies who need to standardize ML workflows. And then once you actually have your MLflow model saved, you can reload it by just passing in a hash associated with each of your experiments. And then furthermore, if you want to deploy, you can use that Spark UDF technique by once again passing in the hash of the experiment and then registering it as a UDF, which in this case we're just applying to a vector in Python. But again, you could use it in SQL. So this is a great answer to how to democratize ML usage within your company. Generally, the approach I've seen here is people use REST APIs. But I think using something like SQL is so inventive because everybody knows SQL. It's actually something that even business analysts can generally apply. So for all the data scientists who create a lot of models but then can't get the rest of the organization to use it, turning it into a SQL function in Spark, I think, is a really good answer to that question. So wrapping up here, I mentioned at the beginning that one of the hardest parts about data science and production is not really the models, but the plumbing. And I showed you a few quick solutions that should provide at least 10x the value for relatively little overhead to change. But I think the really interesting question is, why is plumbing such an issue? Especially since modern software engineering has spent so much time trying to provide tools to simplify the plumbing process through microservices, RESTful APIs, containerization, you name it. And yet, ML production pipelines continuously get stuck on this step. The reason I believe that we're running into this issue is that the fundamental tenet of software engineering is all about decoupling. When we have a big, hairy problem, we want to break it into smaller, independent pieces that are loosely coupled in order to retain flexibility. However, with machine learning systems, there's a fundamental coupling between the data, the models, and the architecture. So decoupling that is a bit of a false breakdown. When I came up with the abstract for this talk, I talked about ML factories. And basically, the idea there was people focus too much on specific models when we really need to raise our thinking up a level to dealing with these ML factory objects containing the models, the data, and the state of the overall architecture. When you miss any of those, your system breaks down. If the data changes, your model should change. If the model and the data stay the same, but you go from GPUs to CPUs, your results might change pretty dramatically. So when we actually take a step back and look at what MLflow actually provides, I would argue it's providing this ML factory idea, where an ML project in MLflow is actually taking a snapshot of your model. It's taking a snapshot of the system settings. And once you join in the Databricks Delta, it's taking a snapshot of the data. I think this idea is super interesting, and I'm excited to see where we go with it next. After having lots of conversations with the MLflow team and our co-founders, one pattern seems to arise, is the idea of data flow. We saw this with TensorFlow, where you have tensors being passed, and you have these stateful nodes. I think MLflow is going in that direction, and I think it syncs up very nicely with the fact that Spark has this lazy DAG execution model. Delta has a lazy DAG execution model on top of data. And now MLflow, when you package many MLflow runs together, you start to see a lazy graph execution model across these ML objects that I'm discussing. So I think that's where the future is headed. I'm curious to see what's coming next, but I think it's time for questions. So thank you very much.
Hi. Thanks you for a very interesting talk. I have a question about MLflow.
Yep.
Specifically about, you talked about decoupling, right? So about decoupling the feature vector from the model, from like the quick introduction that I saw with MLflow, and I play with it a little. When you save a model, you save the model itself with different flavors. It can be sklearn, Keras, TensorFlow, whatever.
Yep.
But I didn't see like the option to decouple the featureization, creating the feature vector in a separate kind of model so that you can decouple that part. Because like when you save the model and maybe you want to use a different featureization script or stuff like that. So I wonder what's the direction about like stuff like that, or if there's like some BKM.
So your question is how, by the way, I was talking about coupling rather than decoupling. Do you mean to say coupling?
You said that software developers
yes.
think about decoupling. So as the data engineer,
but OK, just to clarify that last point, software engineers think about decoupling, but I think that's exactly why we run into so many issues with ML pipelines. Because fundamentally, within ML, the coupling between the models, the data, and the architecture is a feature, not a bug. It's what drives the power behind ML models. So there was actually a Spark Summit talk this summer by Andre Karpathy, the head data scientist at Tesla, where he talked about the need for a software 2.0 that supports a very different development path for machine learning models compared to the traditional software engineering path. So to go back to your question about how do we handle if we have a certain model and we want to try out different feature vectors in our model, how do we decouple the two? That was your question, right? At present, there's not great support for that just with MLflow itself. But as you saw in Michael Armbrust's keynote yesterday, Databricks has a product called Databricks Delta, which provides data lineage, essentially. So in the same way that Spark has that DAG, where it can always rewind if an operation fails, Delta tracks deltas of operations on top of data and builds out a big graph that can rewind for each atomic step on the graph. So when you combine the two, Delta and MLflow, you have the data at a very specific point. So there's a unique hash with that associated with the MLflow experiment hash. And then that's where that coupling comes from. And that allows you to point to an experiment and then actually run that experiment on the exact snapshot of the data as it was when the experiment was originally run.
Thank you very much.
Yep.
Time for 2 more.
So I'd like to continue on this because I was wondering about this feature engineering question also.
Yep.
So you explain how you can go, how Delta shows you the difference between 2 data sets after you, I don't know, you did some kind of operation on your data to engineer your features. Let's say, I don't know, you apply some kind of transformation. So I can see the difference between these two, between the data set before and after. But now I'm supposed to reverse engineer what the operation was that I did, because I'm not storing, MLflow doesn't help me in capturing the operation that I did, only the input and the output. Is that right?
So Delta does. MLflow by itself currently does not. With Delta, we're actually we're capturing the operations on top of a data set, starting from the very raw form all the way to present. And at any point, we can inspect those deltas and say, OK, write this out, explain it to me in SQL. So when you combine the two, I think we get there, but not with MLflow directly. Yep.
Time for 1 more.
Hi. Are there limits on the sort of models that you can sparkify, so to speak, with MLflow? So say, this kind of is coming back to what you were saying about data scientists being sort of reluctant to move on to a new system. I work with a lot of people who are very familiar with single node OR, but the bulk of our production code is PySpark.
Mm-hmm.
So could I, with MLflow or something like that, let them train a model in OR and then register that as a Spark UDF to push through PySpark from then on?
Let me make sure I understand that question. So you're saying, does something like MLflow totally eliminate the need for data scientists to move into the distributed because they can just train single node models and then you can pass it via the UDF into Spark?
Essentially, yes. I understand there are probably limits, but to what extent will the limit affect them?
Got it. So the question of maybe at what point should data scientists go from single node to distributed? I think that's at the root of it. Basically, when I meet data science teams, I don't like to say, hey, you should just switch over to Spark ML, because there's an increase in complexity that happens when you go from single node to distributed. Furthermore, there's that big hit that comes from changing your existing workflow and losing out on common Python or R libraries, which is non-zero. So usually I like to meet data scientists at their environment and say, hey, if you want to get data from Spark into Python, great. Use these 2 pandas things based on Apache Arrow, and it's going to be a lot faster. Or if you want to make your stuff in pandas, but then it's getting really slow to apply the pandas, great. Use a pandas Vectorize UDF to take your pandas functions as is and then apply them to Spark. So this is to meet the data scientist at their environment as much as possible. That said, depending on your models, getting more and more data becomes more important. Or on the flip side, if you don't have any complex data science yet and you're just starting out with a very, very big data set, then maybe it's actually less complexity to start with Spark ML. That's really something for your team to decide. Usually when I'm working with clients on making this decision, we actually start by coming up with various baselines and then establishing in a classification case what's the economic benefit for increases in true positives or the cost for false positives, et cetera, et cetera. When you establish a baseline like that, then you can make arguments. OK, if we move to distributed ML, our performance drops a little bit like this, but it simplifies the data engineering pipeline. How much money do we lose in that performance drop versus how many engineering hours do we save with the reduction in complexity. So I think that's usually how we have those conversations, but it's very specific to every company.
That's all the time we have. Let's go give Thunder another round of applause.
Thanks, everyone.